Hi everyone, my name is Sahra Shakouri. Today I'm going to present you our research about the life cycle carbon footprint analysis and compare the result of a case study with different materials used for structural design. First, I'm going to start with a brief introduction, then explain the materials and method which is used in this study, and illustrate the details of a case study, then show the results of the life cycle assessment for each case, and finally conduct and compare the results. As all we know, global warming is one of the most important and challenging problems of humanity nowadays. Human beings consume energy to extend their lives, and a large portion of this energy produced by burning fossil fuels. Pollution due to burning of fossil fuels lead to increase in the amount of greenhouse gases in the atmosphere. Glaciers melting, sea level increase, and extinction of species is some of the consequence of global warming. Different sectors have roles on the carbon dioxide emission to the atmosphere, and due to the studies, buildings, and construction industry is responsible for the large portion of this carbon dioxide emission. Also, 15% of world's freshwater withdrawal and 25% of world's wood harvest belongs to these two sectors. Also, if we look at the share of different materials in the carbon dioxide emission, it can be noticed that the large portion of carbon dioxide release is related with steel and cement production. As it is shown in the picture, the life cycle assessment is a process of evaluating the total effect that a product has on the environment over its entire life. This entire life could be imagined as cradle to grave and cradle to cradle types. In the second one, the recycling process of used material is also considered. What are these environmental effects? These environmental effects can be grouped as carbon footprinting, water footprint, ecosystem quality, natural resources, and human health. In the past, there were lots of factors impacting the structural design, like lateral load resisting systems, material of the structure, height of the structure, architectural requirements. But no one cares about the environmental impact of the structure in the past. But recently, lots of papers and studies consider the environmental effect of material we chosen for building and constructions. Here you can see the brief list of some studies and some papers. For example, one of them compare timber and concrete, the other one compare concrete and steel. And finally, all of them agree that wood is the best choice as a material for the building and constructions according to environmental impacts. As a case study, a building with the area of 25 meters square and height of 3 meters, which is located in Ankara, Turkey, is designed. This building has a lifespan of 50 years, and this building designed first with concrete, then with steel, and finally with the timber to calculate the life cycle assessment for each case and compare the results. But the foundation and wall system and the electrical and mechanical system are the same for all three designs. In the case study 1, the structure design with the concrete structure design according to Turkish standard No 500, live load and dead load of 2 kilonewton per meter square is applied. A two-way slab of concrete with the height of 15 cm is assumed for ceiling. For fulfilling the minimum requirements in the standard beams with height of 45 cm and width of 35 cm is designed for transferring the load to the footing. 4 columns with the side of 35 cm is designed. C25 type of concrete is used for all the sections, and roughly the amount of steel for reinforcing the concrete is assumed approximately about 1 ton. Steel structure is determined according to Turkish steel design code. The same loading principles are applied to the structure. 5 cm height reinforced concrete slab on a steel trapezoidal deck is designed for ceiling. In order to simplify the design and prevent use of cross beams in the structure, for column, square-shaped steel boxes with side of 15 cm and thickness of 8 mm is used. Main beams in the surrounding is assumed as IPE 180 and secondary beams designed as IPE 120. For this case study, same foundation and wall system is applied. For the third case study, the building designed with timber. For timber structure, material class of C40 with density of 500 kg per centimeter cube is chosen. The structural element designed according to Eurocode 5. You can see the detail of columns and beams for these designs in the picture, and also the 15 centimeter thick timber slab is used for decking. For applying LCA for each cases, OneClick LCA plugin for Revit Architecture is used to perform LCA process. This plugin is based on EN 15978 standard, which is in line with ISO 14040. Environmental Product Declaration means EPD tools used in the analysis are based on EN 15804 standard. EN 15978 supports baseline methodology, which is a database that contains characterization factor for LCA in European market and all assessed environmental impact categories. ISO 14040 standard describes the framework of LCA that includes raw material extraction and production, distribution, use, recycling, and disposal with all transportation activities. The life cycle stages are defined in OneClick LCA covers life cycle stages from cradle to grave with these 5 main stages shown in the figure, as you can see. A1 to A3 is the product stage of construction material that include emission generated from raw material extraction, their transportation and manufacturing process, as well as the waste formed in the production process. A4 is the stage of transportation to the site from manufacturer in which exhaust emission and environmental impact caused by transportation are included. A5 stage includes the emission and environmental impact during site operation specific to the selected material itself. B1 to B8 covers the emission caused by the maintenance and operating stage that is related with the energy used within the building, as well as energy produced externally by the system in the building. C1 to C4 is the construction stage that involves the impact of processing recyclable construction material, followed by waste recovery. In this study, product stage A1 to A3, construction stage A4 and A5, and end of life stage are included in the EN system boundary of the assessment. Operational energy and water stage are excluded from the results due to the availability of the impact categories and rough assumption reached for inventory analysis in Turkey. D also is additional stage which can be included in the system boundaries. However, D includes supplementary information out of building life cycle, that is cradle-to-cradle approach, including the benefits and burdenness of disposal after demolition. In this table, we can see the quantity of consumed and waste material for each cases, for concrete, steel, and timber. There are different waste factors for each material, and also The transportation distance for each material assumed as 15 kilometer for each commuting, and also mixer truck for ready-mix concrete, and 3.5 ton delivery van and 7-ton delivery truck are used for transporting the material to the site. After applying OneClick LCA for each case study, 6 impact categories are specified. Each of the impact categories describe the effect of substances in the environment. However, global warming potential represents the impact of greenhouse gases in the atmosphere, which is commonly used and often called carbon footprint. The unit used, as you can see in the table, for global warming potential shows the amount of carbon dioxide equivalents of various greenhouse gases. If the global warming potential of each case study divided to the area of each building, which is 25 square meter, the amount of carbon dioxide emission for each case is showing below. You can see that concrete has the most effect, and it still has the lowest effect on the carbon dioxide emission. Also, the results show that the main source of carbon dioxide belongs to product stage, means A1 to A3, and end of life stage follows it with considerable differences. All three cases have a close carbon dioxide emission in the production stage, but the portion of C1 to C4 deconstruction or end of life stage is at the highest in the timber case compared to the other two cases. Also, the carbon footprint of the site transportation and installation of concrete is the highest due to the vehicle types used for the amount of materials and waste produced by process. Since a smaller vehicle is used for transportation to site and less waste is produced in steel and timber frame structures, they have a slightly less carbon footprint of A4 to A5 stage compared to concrete framed structures. Also, according to European Commission, embodied carbon for residential structure is categorized into 6 groups between A for the best scenario and F for the worst situation, specific to the building type and location based in order to monitor the energy content of building materials in the domestic market, as you can see in the picture. The results shows for these case studies that steel with the least embodied carbon is placed in the B group, and timber and concrete with similar embodied carbon are placed in the C groups. As a conclusion, it can be said that many factors like EPDs and PCRs and lots of other factors play roles in the environmental impact of a material that is intended to be utilized in the architectural design. But two important results from this study is that because timber is a natural material, it does not mean that it's the best option for all the structures and all the designs. And also, steel frame structure has the lowest environmental impact for this study. Maybe by changing the study and the design of the building, the results could change for each cases. Finally, thanks for your attention. Have a nice day.